Right, now we're gonna prove things on the arithmetic progressions. So the most well-known theorem in this area is van der Waerden's theorem. So let's start with the definition of arithmetic progression. So what is an L-term arithmetic progression? Let's write LAP is a set of numbers of the form a plus d, a plus 2d, up to a plus l minus 1d for sum a and d. D is non-zero, okay, because if d is 0, you have the same numbers all the time. So let's eliminate the case. So what is K coloring? So K coloring or R coloring, a set A is a function. It's any function. It's chi from A to 1 up to R. So let's write. I have been trying to avoid this notation. Let's write the bracket R as this thing. Okay, this is common. Now, here's the theorem due to van der Waerden. Who is a Dutch mathematician in 1927, and he proved the following theorem. So for every K and L, there exists a positive integer n such that every K coloring of n, for every K coloring of n, there is a monochromatic L-term arithmetic progressions. So by monochromatic, I mean every member has the same color. Okay, and this was initially asked by Schur, and then van der Waerden heard from a student of Schur, whose name is Bode, and then so when van der Waerden wrote a paper, the title of the paper was a problem of Bode, but actually the problem was originated from Schur. So we write, let us write W LK, right, be for the minimum, right? So K is the number of colors, that's length, minimum such integer n, and this is called the van der Waerden number. And if you remember this compactness principle from the previous chapter, you will be able to see the following. So the van der Waerden theorem is equivalent to the following: any K coloring, any partition of the set of positive integers. Should I write n? So n is a set of positive integers, not including 0, into finitely many sets in any partition, there is one of them. Okay, one of the parts contains arbitrary long arithmetic progressions. I didn't say that I have infinite. I mean, I didn't say that I have infinite arithmetic progression, because it may not have an infinite arithmetic progression, but there's one particular color that contains any length, like 100, then there's 1,000, there's 1,000,000, there's 1. And one direction is easy if you have the finite version, the previous version, right? If you have this version, then for any length you have one of the colors, right? And then one of the color appears infinitely many times. One of the colors will be chosen for infinitely many lengths, and that's the color that we'll take here. What about the converse? The converse is where you use compactness principle. So you take the hypergraph whose vertices are the positive integers, and the edges are the length. Edges are the arithmetic progressions of length L, and then think of the chromatic number, right? And then you use the theorem in the previous section to deduce that such a number n exists. All right, but I'm not going to use this principle. Let's see how we prove the van der Waerden's theorem. We're going to use induction. Right? But we will have a stronger statement. So let XLM be the set of all sequences X. Let me write it as X1 sequences X in there 1 L to M, so sequences of length M, right? But you can think of it as a function, right? So you have X1, X2, XM, right? So X is equal to something like this, such that if Xi is L, then Xj is L for all j bigger than I. So I'm collecting all the sequences of length M, but whenever I have L at some point, then in the remaining everything is L. So I collect all these things, and that's XLM. And we say two sequences let me define XM. So XM is gonna be no X. Two sequences XY in XLM are L equivalent if there exists I in 0, 1 up to M, M. Oh yeah, I is the locations, such that xj is not equal to jx, yj is not equal to L for all j less than I, and xj yj is equal to L for all j greater than or equal to I. So two such sequences are equivalent if the location of the segments starting with L is same, right? So here you don't have no L, and at some point it starts with L, but this location is same, then these two are equivalent. Now XLM is partitioned into m plus 1 L equivalence classes, right? Depending on the location of the first position of L. So one possibility is that maybe L never occurs, or L occurs on the first position, second position, etc. So I is the number that where L start. So there are m plus 1 possibilities. So that's why you have m plus 1 equivalence classes. Now we have a stronger claim, which will be enough to prove the van der Waerden's theorem. So claim for L, M, and K, there exists some integer n, which is a function depending on L and K, such that for every function C from this set L M, from all the integers to, so for simplicity, I'm gonna change the coloring. Instead of using colors from 1 up to k, I'm gonna use colors from 0 up to k minus 1. This doesn't change anything, right? So C is the coloring, k coloring. There exist positive integers a, d1, d2, dm, such that see when you evaluate this function for all numbers of this form, a plus sum of xi times di, this is constant on all sequences in each L equivalent classes, in each class of XLM. So that is claim, right? So whenever I have a function coloring, so k coloring of the positive integers from 1 up to n of n, I can find these parameters a and d1, d2 up to dm, so that if I take any sequence xi, x, in one particular equivalence class, L equivalence class, the value of that is independent of the members, independent of choice of x, right? And what this claim implies the van der Waerden theorem. Let me write VDW for van der Waerden, because when you take m is to be 1, then but this claim implies that C of A plus sum of xi d1 is not a sum. It's this. This is constant. But among there are two L equivalence classes. on XL1, right? One is, so XL1 consists of the following. So you have one sequence where you don't have any L. So but sequence has length 1, so it's 0, 1, 2, L minus 1. That's one equivalence class, and another equivalence class is you have 1L, and that's it. So there are two equivalence classes, 2 L equivalence classes. And if you plug in this first equivalence class, then xi is what? You put 0, you put 1, 2, 3. So this implies, from here implies that C of A plus D1, no, C of A plus D1, C of A plus D2 D1, C of A plus L minus 1 D1. All these things are equal because this claim says that this is constant. Okay? So that's why this claim implies Van der Waerden's theorem. And it's a bit stronger, right? Not only you have 1 D1, but you have a D1 up to Dm. You can find these things. Now, and this actually makes the proof easier. Suppose the claim is false. So we're gonna use double induction. So another way of saying it is I'm gonna use minimum count example argument, and I'm gonna choose parameters, some instance where some parameter is minimum, and then among all count examples with that achieving that minimum parameter, I'm gonna choose another one, another parameter to be minimum again. So choose a count example with the minimum L. By this choice, I know that the theorem is true. I know that the claim is true and L is smaller. And among all of them, with the same L, we choose the one with the minimum M. And when L is 1, then it's trivially true. Why? Because when L is 1, L equivalence classes is just 0, right? I mean, each L equivalence class is either just 0 or 1, right? No, I mean length is M. So XLM is partitioned in the equivalence classes, but it looks like 0, 0, 0, 0, 0, or 1, 1, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1, 1, 1, right? Each of them has only one sequence in each equivalence class, so the value is constant. So each equivalence class has only one sequence. So now I can assume that L is bigger than 2, and L is bigger than 1. Now, let me first treat the case when M is not 1. Then we're going to take M, capital M, to be this number given by the induction. This M minus 1 is smaller than M, so I know that this number exists, right? And then I'm going to take M prime to be n of L1 k to them, and then n to be M times M prime. And this number exists because this 1 is less than m, and so I can make a product of these two numbers. So suppose C is a coloring from n to 0, 1 up to k minus 1. Now define C prime. Now I'm going to define a new coloring of the integers from 1 up to m prime to 0, 1 up to k to the m minus 1 as follows. So that C prime of x, now you can think of the base k expression of the integers. Right? So if k, like if k is 2, it's like 1 and 2 and 2 to the 2, 2 to the 3, 2 to the 4, etc. I mean, we have like a number of available colors is k minus, I mean k, and we're gonna put some c of something here. And what is that? That is x minus 1m plus I. So in other words, I have integers m prime integers, and I'm split. So this was a C function. I'm splitting into intervals of length m, right? And then my C prime is coloring for m prime integers, and the color of this integer will come from here, right? By using this expression. And this is bijection, right? Whenever I have integers, right? Whenever I have integers from 0 to k to the m minus 1, I can write it as base k expansion, and then we can determine the coefficient that will give the color over C. So C and C prime are like same animal, right? Just compressed or expanded, right? So we can deduce that if C prime x is equal to C prime y, then C of x minus 1m plus I is C of y minus 1m plus I for all I from 1 up to m. Okay, now we're going to use this assumption. So by the assumption on n of L1 k to the m, right? You have this assumption, right? N of m prime. So what do we know? There exists a prime and d prime, which is positive, such that C prime of a prime plus okay, let me write this way: C prime of a prime plus d prime, C prime of a prime plus 2d prime, and C prime of a prime plus, now what is the length? L minus 1 are all equal, right? So we find so in here, in this long interval, I find some blocks where this is same as that and that's same as that. So the color when you follow the same locations, the colors are same. Right, so that's first step. Now, how do we find the correct one for like I mean we need to find the d2 to dm. Yeah, now we consider one of these interval, the interval. So here's a prime, right? I mean the interval corresponding to a prime, so that's like a prime minus 1 m plus 1 up to a prime minus 1 m plus m plus m, right? So you have m integers by the assumption on m there exists a and d2 d3. So I'm intentionally omitting d1 because I'm getting, so m is what? M is n of L m minus 1 k, right? So I can find a and d2 d3 dm such that a is in this interval, right? So what I got is inside here I can find such a thing. So a is in this interval. I mean not only a but a okay, let me write a plus sum of xi di from this thing for all x in an L equivalence, for all x in each L minus 1 equivalence classes, right, of 0, 1 up to L to the m minus 1. Now from here we deduce that, and also we know that C of A of xi di is constant, right? So what I know is that inside in one block I can find the good selection of A and D1 A. I find A and D2 up to DM. So inside here I have some good things, so that whenever I have L minus 1 equivalence class, the value of C is independent of the choice of the members of equivalence class. Now, if we have an L minus 1 equivalence class, then when I attach x1, I still have L minus 1 equivalence class. So this implies that let's observe the following. CA plus sum of xi di from 1 up to m is constant on every now L equivalence classes. Of 0, 1 up to L. Right, here's M. Because when I have a sequence, if this is length M, if this is L, then everything here is L. Or if this is not L, if it's not L, then it could be something coming from x L minus 1M, right? So the equivalence class here will determine the equivalence class here. And equivalence, in this case, equivalence class is just 1, right? All right. And yeah, so that's it. So the claim is proved if m is not equal to 1. And we already assumed that it's a count example, so I should say it's contradiction. Thus, we may assume m is equal to 1. Now, in this case, let n be the NLKK. And suppose we have a coloring function. C is coloring from n to 0, 1 up to k minus 1. Then there exists, by induction, A and d1 up to dk such that a plus xi di is at most n, right, k, and c of a plus sum of xi. Yeah, xi di is constant for all for x in each L equivalence class, right? Right? Actually, I made a mistake here. Yeah, so instead of L, I should say L minus 1. Yeah, so here's, let me write it in red color. So it's L minus 1. Yes. Okay, so each, and I should say each L minus 1 equivalence class. Right, so, oh, this is actually XL m minus 1, right? The length is yeah, length is m. I was confused here. All right. So the xi is numbers from 0 to L minus 1, right? So xi, remember, x is numbers from 0 to L minus 1 up to k. Now, what are we gonna do? So we have yeah, we have a and d1 of the dk, right? And so what we're gonna do is to find the pair, right? Now let's consider the following. So C of A plus L d1 plus d2 plus dr, C of A plus L d2 plus d3 plus dr. d2 d3 dr c of a plus l d3 plus d4 up to dr and c of a plus dr and c of a LDR. So how many terms do I have? I have r plus 1 values, right? Oh no, where's that? What is r? No, it's k. Right? So I have k plus 1 values. But C is a function. C is coloring with k colors. Right? So by Pisonal principle, two of them are equal. So what I mean is, I can find there are u and v. Let's say v is less than or equal to k plus 1, and u is at least k, at least 1, such that the sum c of a plus u to r, u to k, d yeah, u to k l d I, no, l di is equal to c of a plus v to k l di. All right. Now, what are we gonna do? Now consider c of a plus v to k l d I plus x and okay, let me say this way, xi 1 up to v 1 up to v minus 1 di, right? So here, this is what this is. So that's what we're gonna take as d1. So we will take a prime as a plus sum of l di from v to k, and d1 prime as sum of the di from 1 up to v minus 1. Now, there are two cases, right? We claim that ca prime plus x1 d1 prime is constant for every L equivalence classes. Why? I mean, the reason is, right? So there are only two possible reasons. I mean, two possible things. M is 1, right? So what are the equivalence class? So XLM, that only two equivalence classes. Either it's 0, 1, 2, M, L minus 1, or it's just L only. But in this case, you only have one sequence So there's nothing to prove. So the only case you're worried about is this case where you're putting values 0, 1 to up to L minus 1, right? And if I put the value like 0, 1 up to L minus 1, what's going to happen? Oh, I see. I now realize where it goes wrong. Okay, let me fix one more time. Because these L, I'm going to replace it by L minus 1. Okay, so this is going to be L minus 1, this is going to be L minus 1. Yeah, now it looks better. Okay, now when I take, for instance, this value, what we can do is I'm thinking of a sequence in the previous case where I put 2, 2, 2, 2, 2 and L minus 1, L minus 1, L minus 1, right? Okay, right, we are looking at the color, right? So what I mean is we look at the colors of the following things: C of A plus, A plus, and then we have in zero case what we have is, okay, here's the L minus 1, so L minus, oops, let me erase this. So L minus 1 dv L minus 1 dv plus 1 up to the L minus 1 dk. That's one instance. And I know, and then if it's 1, what I am doing is d1, d2, and dv minus 1, and then same thing. If it's 2, and then same thing, right? Now we are comparing all these values. Are they equal? Right? Why are they equal? The thing is, all these sequences, so this corresponds to sequence 0, 0, 0, 0, L minus 1, L minus 1, up to L minus 1. This is 1, 1, 1, 1, L minus 1, L minus 1, L minus 1. This is 2, 2, 2, L minus 1, L minus 1. They belong to the same L minus 1 equivalence class. And by induction hypothesis, I know that they will have the same value. Right? I know that they have the same value. It's constant over every L minus 1 equivalence class. Except there's one case where it doesn't belong to the same L minus 1 equivalence class. That's when you have L minus 1 d1, L minus 1 d2, L minus 1 dv minus 1, and then you have L minus 1 dv up to L minus 1 dk, right? But this is exactly why we chose v as that, because when you look at this, that color is same as the color, right, v to k is same as u to k. Okay, so what does that mean? That means I see. Okay, sorry. Again, I think I still want to fix it. So here, let me replace this by, let me choose u, and then here is u. All right, so this is from U. Now it's better. All right, let me try again. So this is 0, 0, then 0, 0, and from U, I'm starting U1 plus 1 up to D V minus 1. So, and then we have 2, 2, 0, 0. So this is 2 du plus 1 up to 2 dv minus 1. And then, so all these things, you start with the u minus 1 zeros, and then from u places you have two same value like k, or no, not k, but x, and then you have l, and all these things are l minus 1 equivalent, except you have this case, except you have du plus 1 of that. So that's 0, 0, and then l minus 1, l minus 1. So this is u, and then, right? But this is what? So this color is equal to C of A and L from V to K, right? And that's the same as this thing. Oh, it's L minus 1. So we chose these two are equal, right? That's the choice of UMV. Yeah, when you choose UMV, we chose by Peason's principle that this is happening, right? So that's why this works, right? So on every L equivalence class of this thing, this value is constant. Now let me tell you some historical things. So on a related problem, here's a conjecture by Erdős and Theorem in 1936 that every set of positive upper density. So what is positive upper density? Well, you can think of the limit of the density of set, number of integers inside A divided by, number of integers of n most n inside A divided by n. That's density. Then you take a limit as n goes to infinity, and then take a lim sup. That's upper density. And then every set of positive upper density has a 3-term arithmetic progression. So this is stronger than Van der Waerden theorem for 3-term arithmetic progression, because when I partition the set of positive integers into 3 colors, one of them will have at least 1/3 of the all positive integers. So you have a positive upper density. In that case, inside that set, Erdős and Theorem thought that it must contain 3-term arithmetic progressions, which is not guaranteed by Van der Waerden theorem. Van der Waerden theorem says that one of the color classes has 3-term arithmetic progressions, but not the biggest one. It could be smaller one. And this was proved by Ross in 1953. And this proof implies, this proof was using can be proven with various methods. There are combinatorial methods, there are methods using Fourier analysis. And then in 1957, Erdős conjectured a stronger statement, conjectured that every set of positive upper density has a L-term arithmetic progressions. Now, this was proved by Semeredi in 1975. And this is where Semeredi invented his famous regularity lemma, which is one of the main achievements made him to get the Abel Prize a few years ago. And later, this theorem has been, so Meredith's proof was using van der Waerden's theorem and also using a combinatorial method. And then 1977, also proved by Furstenberg, but using Fourier ergodic method. I'm not gonna, I mean, I don't know exactly what it is, but using different method, not combinatorial. And there's even a very strong theorem. Let me simply state the theorem by Bergensen and Liebman in 1996. So let's say instead of arithmetic progression, now you have a polynomials with the integer coefficients, with the non-zero, zero constant terms. If A is a set of positive upper density, then there exists, then there exists A and D such that A plus P1D, A plus P2D, A plus PKD, all of them are in A. And this implies a lot more strong theorem. For instance, if I partition a set of positive integers into finitely many sets, then I can always find one set which has A and A plus P1A, A plus P1D, A plus P2D, etc. So this is called the polynomial van der Waerden theorem. There are combinatorial proof of this polynomial van der Waerden theorem, but this particular proof, there's no combinatorial proof known. The only proof is using ergodic method. So the current best bound for van der Waerden number is actually due to Tim Gowers, 2 to the 2 to the C to the 2 to the 2 to the L plus 9 by Gowers in 2001. And but this proof is not using combinatorial method, it's based on Fourier method. There is a proof using a combinatorial method. So this is 2 Graham and Solimorsi. But this is just for 3-term arithmetic progression. It gives you something like this. This was 2006. So here's another conjecture, Erdős conjectures, with a $5,000 worth, that if, instead of saying positive upper density, if one of the, if you take the if you take a sum of the 1 over A for all A elements in set A, then A contains on L term arithmetic progression for every L. And this is still open, but Ben Green and Terence Tao in 2004 proved that it's true for the case when A is a set of primes. It's well known that sum of the 1 over prime is infinite, and it was not known whether it contains L-term arithmetic progression until 2004. So this is one case. Anyway, that's it for van der Waerden theorem. We're going to prove the much more general version in the next lecture.